understand also. This video need not to be recorded. After that, you can record it and mail submit. It has three terminals. This is known as anode, this is cathode, and this one is known as gate. Okay, in the video it is mentioned that one engineering scientist has invented this one. Who is that person? You told me you have watched the video. It is mentioned that someone invented these thyristors. Who is that person?
Sir William Shockley.
William Shockley. In which year he has introduced this device?
(1956, 56).
No, 1950. So, and before introducing this one, so in this video, they mentioned that this thyristor actually, when it was introduced, after that it was massively used for a particular application. What was that application? They have given in this video an example is given for
High voltage DC.
High voltage DC, HVDC, right? HVDC transmission. Are you familiar with the transmission line?
Yes, sir.
Suppose this is your generating station of power. Generating station. So it produced power. And then in our country, what we do, we step up this. Step up the power. And this is your transmission line. AC transmission line. And then at the end, we use another step down transformer. Step down. If it is a grid line, have you seen there are some big towers by the highway? They have in our country, we have a grid line with high voltage transmission. Do you know the range of the voltage? What is the voltage of this transmission line in the grid system? Any idea?
$33, sir. 33 kV.
No. The voltage is in some is 230 kV. In some cases 130 or 132, I forgot. Very high voltage transmission. Do you know why the voltage has been raised or step up? What is the reason behind it?
For power loss.
Why the power loss is there? If it is, suppose the generator, it is producing 6.6 kV. If we want to transmit this 6.6 kV, then what is the problem?
It will have more power loss.
Why?
Because of the resistance of the line.
Yes, resistance of the line, and then if we transmit this 6.6 kV voltage through your transmission line, then what is the problem? And when it is 130 sorry, 230 kV. And what is the advantage then? You have to answer very, very clearly. So section B, please answer. And this is very, very here, but in section C, section A, almost every student, 3 or 4 students would not join. You don't care about this class, right? Section B. Okay. No problem from my side. So tell me, what is the advantage? Why the voltage is a step up in the transmission line?
So if the voltage is stepped up, current will be less and I square R loss will reduce.
Why the current will be less?
Sir, because ওই যে power এর সূত্রটা
Sir, in step up
One power same
transformer, the voltage steps up, but the current steps down.
Okay, so if this power is P1, if here is P2, so if it is lossless, then P1 must be equal to P2, then V1 I1 must be equal to your V2 I2. So if this one is constant, then if you increase this voltage, then this current must be decreased. Right? If this current decrease, suppose this is the current I2, if this current I2 is decreased, then power loss I2 square R will be decreased, right? That is why this has been stepped up for the long transmission line. And because of the, if this transmission is AC, there is some effect. Corona effect, there is some corona effect. Corona is that it is also for the DC. This is the problem of like it is ionized the surrounding air, and there are some skin effect. Are you familiar with the skin effect?
Yes, sir.
What is the skin effect?
Sir, in case of AC voltage, the effective cross-sectional area through which the current is flowing, it gets reduced. So, sir, that's why we get
Right.
more resistive loss.
Yeah, and also we need the transmission line width must be increased. So,
Yes, sir.
so it is also expensive. So because of all those things, for a very high distance, long distance transmission line, this HVDC is preferable. But in our country, we don't have this HVDC, but in USA, in Germany, and also in some European countries where the transmission line is more than 1,000 kilometers, they use this HVDC. So this HVDC, as in the video, it is mentioned that here they use a AC to DC transmission converter. They use AC to DC converter. So then this one, this becomes DC, and of course it is high voltage because they stepped up before that they stepped up. So what is the converter that we have learned for this AC, to make it the AC voltage to DC? Any idea?
Sir, there's some noise in the background.
Yes, this is not from me. This is from some of you. Okay, I am asking you, what is the name of this converter which makes AC to DC?
Pacifier.
The rectifier.
Rectifier, okay. So before this vacation, we have learned one kind of rectifier. What is the name of that rectifier?
Sir, can you repeat that?
So
Bridge
my,
rectifier?
no, this is the, yes, bridge rectifier, of course, but that was uncontrolled line frequency, uncontrolled rectifier, right?
Yes, sir.
So which device we have used for this?
The diode.
Right. Diodes are used.
We use 4 diodes.
4 diodes for the
To build a bridge
but-
rectifier.
but we can have 2 diodes, right? Also
Yes, sir.
for another type of rectifier where the center tap transformer is used, right? Am I correct or not?
Yes, sir.
Okay. So uncontrolled rectifier. CRs, next time, if the students is less than 40, then I will not take the class. You will collect the video from section C or section A, and then from that you will learn. I will not take the class if the number of students is less than 40. So you just convey this message to your friends. Okay? Because it seems like if the students does not want to come to the class or do not want to come to the class, it seems that you will be able to learn from the video. So no need to take the class for you. I will not take. Thursday's class will be stopped. Okay, uncontrolled rectifier. If it is a bridge rectifier, uncontrolled, that means diode are used here. If Vs equal to √2 capital Vs sine of omega t, pi, this is your twice pi omega t, and this is your Vs. So peak value is then √2 Vs, right? What will be the wave shape of your output voltage? The wave shape of the output voltage will be like this, right? So √2 Vs. And then what will be your DC value? This is your VDC. VO. What will be this DC value? We have already learned in terms of Vs. What is this DC value?
Average value.
Yes, what is the in terms of Vs? In terms of Vs, what is this? Here, what should I write down? You are not serious at all, and you don't care. It will be 0.9 Vs. And I taught these things to you in second semester also. That was 2 Vm by 5. So here Vm is equal to √2 Vs by pi. Just a moment, your VC called me. Can you hear it now? Hello?
Yes, sir.
So if you put this one, use your calculator, then it will come 0.9 VS. So did I tell these things before your vacation?
Yes, sir.
Why you cannot answer them? So look here, our output voltage VDC here. This is fully dependent on the magnitude of VS. That means the peak value of your, or the RMS value of your input voltage, and we don't have any control. If it varies for any reason, of course your output voltage will be changed. So you cannot use this kind of converter in your high voltage DC transmission. So you must have some control so that the output voltage can be stable. That is why we need to use another device. That device will be known as what? I have already given the introduction through your video. What is that device? Hello. In the
Sir,
video.
Can you repeat
Yes.
the question again?
So is it breaking? My voice is breaking?
No, sir, I got disconnected.
Okay. My question is, in the video, they have introduced a new device. What is the name of the device?
HVDC.
No, that is that converter. What is the device they have introduced? They have talked
Thyristor.
thyristors. Okay, thyristors. So thyristors, if we can use this thyristors, and more specifically as here they have mentioned, silicon control rectifier. And if we use this kind of device, then we can control the output voltage. So this thyristor is a 4-layer device, as it is already mentioned in the video. So look, how many junctions are there in this 4-layer device?
4 junctions.
4 junctions.
No, 3 junctions. Sorry, 4 layers.
Okay, J1. This is your J2. This is your J3. Okay, suppose it is a diode. If we think it's just like anode to cathode, if we make a forward biased here, what will be the biasing condition of this junction J1?
J1 will be forward biased.
Just forward biased. Okay. What will be the condition of J3?
It will be reversed biased.
No, N is negative. Look
Oh,
here,
sorry, sir.
N is-
J3 will be reversed biased.
J3
sorry.
will be forward biased.
J3 will be forward biased.
Yes. But this J2, look
J2
here,
will be reversed.
right, J2 will be reversed. So now I'm going to show you the IV characteristics. Suppose this is your VAK and we're varying this. This is your IA and this is your VAK. If we increase this VAK, so this one will be more forward bias, this one will be more forward bias, and this one will be more reverse bias, and there will be eventually there should not be any flow of electron. So current will be 0. But if you apply too much voltage here, eventually this junction will be reverse breakdown. We have learned it in the diode case, Zener breakdown or avalanche breakdown. Then eventually, in some cases, there could be breakdown voltage, say VAK breakdown. That is not our preferable operation. Rather than we want to break this junction J2. How can we do that? In the video, it is mentioned that we shall apply another secondary voltage here. And if we do that thing, then the electron will be supplied from this battery or the source, and eventually this P, there will be lot of electron, lot of electron, lot of electron, lot of electron, lot of electron. So this layer will become the N. So look here, we will get a very big N layer. So then it becomes a PN junction, right? If we apply this gate pulse or gate voltage. Actually, we don't need this gate voltage always. Just if we apply just a pulse like this, then this junction will be broken down and this device will eventually become a diode. So, okay, we are applying a voltage, at a particular voltage, say here. Then we apply a gate pulse. Then what will happen? There will be flow of current like this. And we increase this voltage VAK here, say here. And we have not applied, but okay, here IG, the gate current has been applied. Here then again, for the another case, IG1, maybe we can apply another. So this is one VAK, VAK1, this is VAK2. So in different voltages, we can apply the gate pulse in different time. So we can have that flow of electron just like a diode. That has been nicely described in the video. Who have missed the video, they can always, it is given in your messenger group, you can play and try to listen. Yes, still only 35 students are present. So, okay, from morning, did you have any class?
Yes, sir, one class, numerical methods.
When was it? Is it?
Sir, it was on 10:30 a.m.
10:30 to 11:45?
No, sir. Sir was sick today, so he took a shorter class. It was till 11:15 or 11:20.
Okay, so in that class you were present, all the people are present there?
Sir,
No,
no,
sir, not all were present.
not all were present.
Not all are present, okay. So what is the reason you are not coming, the section C is not coming to the class?
So like some foreigner students, they are out of Bangladesh. They have some issue like
The book, I forgot to open the book. Let me open it. Okay, why use it? Just wait, okay. Is the book is visible? Hello?
No, sir. Sir, no.
No?
No, sir.
Okay, you'll see it right now. Now is it visible? It should be.
Yes, sir. Yes, sir.
So this is the chapter 6 from Ned Mohan. Still Ned Mohan. Third edition. Okay, so we shall cover some of the topics from here. So this is I have already given you the introduction. So this is the line frequency phase control rectifier. Also, it is mentioned that inverter. So line frequency AC to control DC. Now your output voltage you can control by some way. I shall introduce these things to you. And it is mentioned that we use of this device, you can make the rectifier. That means you can make AC to DC. Also, the DC voltage can be also fed back to the input in the form of AC. Then it will be known as the inverters. It is not that inverter like what your prime officer will teach you. That means that DC to AC inverter, but it is depending on the application or control parameters, control strategy. You can always feedback your load voltage or the excess energy stored in the load to feed it back to the input. Okay, I'm giving you the example. Like you know that nowadays hybrid cars are there. So by using the battery, they have used a motor to run the car. Actually, they use inverter, and with that inverter, they use the permanent magnet synchronous motor, and with that motor, they drive the car instead of taking the fuel, petroleum energy, because petroleum is not environment friendly, as well as it is costly. So that battery gives the power to your motor, and the electrical vehicle moves. And particularly when suppose you are moving from top hill to downhill, so you are using a brake, right? So using the brake, you are wasting that energy, but just by in your wheel and brake, there is a brake pad. So there will be, what is that, corrosion or what? There is when you push your brake, then your wheel stops and you can control the speed, but you are just wasting that energy. But instead of doing that, you can always use this energy to charge the battery, and it will be known as the dynamic braking. Did you hear the name of dynamic braking? When you
Yes,
start
sir. Tesla has that kind of
yes. Also in the DC motors, when that has been covered, your teachers should have told that thing. So instead of just putting the brake, if you push your brake, that will not go to your wheel and wastes the energy in the form of heat. Rather than you can always charge the battery. So then your energy will be fed back to the battery, and this is inverter operation, like things is going there. And also there is regenerative braking is there. It is like the same thing. So from the load, your source will be charged. So, okay. We shall study these things here. So it is mentioned that line frequency. So line frequency means that we will take directly the power from the source that our PDB or RAB or the utility is supplying us. And it is phase control rectifier. What does it mean by phase? I am coming to this thing right now. Okay, so now, okay, let us show you first. In the introduction, they have told a lot of things. Like previously, we have used this line frequency. Okay. Why the cursor is not? Okay, let me use this one. line frequency diode rectifiers that were used, but we shall use that control rectifier, and then that control rectifier will be, we shall use thyristors here, and that thyristors, it is mentioned that the light was present in the AC side, and then discover the instant at which the thyristor begins to ceases conduct depends on the line frequency, AC voltage, and the control input. Moreover, the transfer of the commutation of the current from one device to the next nature. Okay, so we shall cover all these things. Okay, so you don't worry, you just read it. The thing is that now, if you look at the figure 6, this is 6.1, figure 6.1. So this is the AC side, and this is your DC side, and we shall use a control rectifier with the symbol of thyristors. Now this one, so that that will be, say, √2 Vs sine of omega t, single phase. It could be 3-phase also. Okay, but we are just right now we will be using only the single phase. And then this VD will not only depend on the, like for the diode case it was 0.9 Vs, but here there will be a function of alpha. That means there will be a triggering angle where we can trigger, and we can always control this. They call it VD alpha. We can control this output voltage. And also here in the figure B, so there are two coordinates we have used. One is the ID. ID is the current that is going to the load, and VD is the voltage across the load. The current will be always positive. Look here, the current is always positive, and it has a limit, maximum limit. So, okay. But the voltage could be positive or could be negative. So PD, the power here, PD will be VD multiplied by ID. So if this VD is positive, that means the first quadrant, and ID is always positive, then this PD is positive. Am I correct or not? You
Yes.
understand? So if VD is positive, ID is positive, that means it is absorbing power and it is working as a rectifier. That is why it is first coordinate operation will be rectification. But somehow if your VD is negative, your current is always positive. This is always positive, but if this VD is negative, look, if this VD is negative, then your PD is positive or negative. PD is negative, right? So the power absorbing by the load is negative. It means that actually it is not absorbing the power, rather than it is feeding back the power. The power will be fed back to the AC side, and then that operation will be known as inversion or inverter operation. Okay, so we shall see all these things inshallah in this chapter and try to understand what is going on. So like your diode, we have studied 3 basic circuits. Can you remember? One is the half-wave rectifier with the resistive load. Another is the half-wave rectifier with the RL load. Another one, half-wave rectifier with the constant voltage load. For the diode rectifier, can you remember this? Hello?
Yes. Yes, sir.
Okay, good. So now I will be using, inshallah, the whiteboard. Okay. So first of all, inshallah, we shall use the resistive load and see how it works. So the basic half-wave rectifiers. First with R load, resistive load. Resistive load. So this is the thyristors we are using, or the SCR, and the load is resistance. and we are using the source voltage here. Vs equal to root 2 Vs sine of omega t. And this is R, and the current is here, say I. Okay, and the voltage here, positive, negative, say it is Vd. If we now apply this Vs input voltage here, the wave shape of the input voltage will be of course sinusoidal. This is your pi and this is your twice pi, and suppose this is omega t. And what is this peak value? What is this peak value?
VM.
Vm is what?
Root over Vs, root over 2 Vs.
Yes, it will be root over 2 Vs, right? This one will be a root over 2 Vs. Okay. So now this is the gate, this is the anode, this is your cathode, and this is your VAK, the voltage across your thyristors. Okay. So with this positive voltage here, the device, that means the thyristor is forward biased or reverse biased.
Forward biased.
So diode is forward biased. The thyristor is forward biased. So it is ready to conduct. So suppose this is your IZ. Did we or have we applied any gate pulse? Like
No,
right
sir.
now? No, not. So what will be the, for this, if IZ, there is no IZ, what should be the switching position of this thyristor T? It will be on or off. What should be the current if you have not applied any gate pulse?
It should be off until the breakover voltage.
That means if it is your anode, if it is the cathode, if it is your gate, so this junction J2 is still reverse bias, right? So there will be no flow of current. If there is no current, what will be your VD?
Sir, VD will be equal to Vs.
If this diode is, the thyristor is not conducting, like if it is open, if it is open, then what will be the current is 0. Your VD equal to current I multiplied by R. If the current is 0, then what should be your VD?
So 0.
It should be 0. So we should not get any voltage, right? Even though it is forward biased. Am I correct or not?
Yes, sir.
Okay, now
Yes, sir.
suppose that omega t equal to, say, alpha. This is the alpha. Alpha could be, say, 30 degree. This is your alpha. We have applied a gate pulse here. So with this region, 0 to omega t alpha, what will be the switching position of your thyristors?
It will be on.
0 to alpha.
Sorry, 0 to alpha, it will be off.
If it is off, then of course we should get 0 voltage, right?
Yes, sir.
The voltage should be 0. Output voltage should be 0. Or VD should be 0. And then we have applied, let's say, IZ at omega t equal to alpha. Then what will happen?
We will get a gate pulse and the current will start to flow. So we will get an output at alpha.
So that means it will be short circuited, right?
Yes, sir.
If it is short circuited, then VD should be equal to your
Yes.
VS.
Yes.
Okay, then your VD should be equal to VS. Okay, let us also plot the current here. Since this is resistive load, of course the current should follow the same wave shape of your voltage, right?
Yes, sir.
Okay, so and since there is current and we see that Vd equal to I multiplied by R, so I has a okay, so sorry for the interruption. Since Vd equal to I multiplied by R, so and it is equal to your Vs, so we should get the output voltage. Just you follow this one here, right? Now, after omega t equal to pi, say pi to twice pi, what is the biasing condition of the?
It will be reverse biased.
It is reverse. And what is the current here at omega t equal to 0? Omega t equal to pi.
It will be 0.
Current is 0 and the voltage is reverse biased. Then what will be the condition of your thyristor here?
It will be turned off. The switch will be turned off.
Turn off. If it is off, then of course we shall your Vd will be 0. So Vd will be 0 from
I
this
pi.
level, right?
Yes, sir.
I to twice pi. So this Hassett line is your Vd. Now I want to plot your output voltage alone. Are you following?
Yes, sir.
Rest of the students, those who are not responding.
Yes, sir, we are following.
These are the basic thing. Okay. So now I am plotting the say this is your alpha. So that is my output voltage, and we should okay, let me use the another color that will make you more understand. This is your root 2 Vs sine of omega t, and this is 0. So I want to find out the average value, Vd alpha. So how we can find out the average value? What is the process to find out the average value? You have to
We have to divide this.
You have to get the area and divide
Area.
with the time
Yes,
period,
yes.
right?
Yes, sir.
So how to get the area? You know the equation.
Yes, sir. From we have to just integrate it over alpha to pi.
And divide it by time period.
Divided by 2 pi.
Yeah, only the girls are responding. What happened to the boys? So whole night you were doing something else and now sleeping, right?
Sir, actually Ashraful is also responding, but he can speak. Date ব্যথা, sir.
Oh,
He's just responding through chat box, sir.
it's okay. So except Ashraful, there should be a lot of Mashraful also, right? So they are not saying anything. Okay, twice pi, then root 2 Vs, then minus cosine of omega t, then pi to alpha, and then if we complete this one, root 2 Vs by 2 pi, then that will be your minus cosine pi is 1 and 1 plus, then it will be cosine of alpha. Am I correct or not?
Yes, sir.
Okay, now Vt alpha is coming as point. If you calculate this, this is 0.9 Vs, and then it will be 1 plus cosine alpha. Is it root 2 by 2 pi is what? 0.45 or what? I think it's 0.45, right? Can anyone do it? Root 2 by 2 pi.
It's 0.225.
0.45, right?
One.
Is it
Sir,
0.45?
0.225. Root 2 by.
Sir,
Root 2 by
0.225.
0.225?
Yes, sir.
Okay. 0.225 ds, this one. Okay, good. Now, to check whether our equation is okay, if you put alpha equal to 0, that means you, instead of alpha equal to say 30 degree, if we apply this pulse at alpha equal to 0, that means here, right? Oh, sorry. If we apply the get pulse here at alpha equal to 0, now alpha equal to now 0. If alpha equal to 0, we can put alpha equal to 0 here. Then it is coming as 0.45 ds, right?
Yes, sir.
So that, and also your wave shape will be like this. And it comply with our concept, half wave rectifier. Am I correct or not?
Yes, sir.
So now you can vary the alpha. You can make it alpha equal to 30 degree. You can make it alpha equal to 90 degree. You can make alpha equal to say 270 degree. You can make alpha equal to very much close to pi. So this is the, and it is with the phase of your input voltage. That is why it is known as phase control rectifier, phase control. So our control parameter is now Vd alpha equal to point, for this case, half wave rectifier, 1 plus cosine of alpha. So this alpha is a control parameter, right? You can control. Yes, so how can I control it? Of course, in this book it is given. Inshallah, next class we shall show you how to control it. You must know the input voltage. You have to synchronize this one with your electronic circuit by using your op-amp. We call it control circuit to generate the alpha. You can, we call it delay angle also, or firing angle or trigger angle. You can make alpha equal to 0. So what is the range of the alpha?
0 to pi.
0 to pi. So until that one, I have covered here with the other section. Okay. Okay. So let us. Can you see the book now?
Yes, sir.
Yes, sir.
Look here. Here, thyristor triggering. I did not cover this in your previous section, so I will not start this one today. But inshallah, next class I shall. We will get only 4 more class. Okay, so I hope I'll be able to do it, or but I may need another 1 class. Look here. This is the circuit, how you generate this firing pulse. These are the firing pulse in here. So you can vary this firing pulse from here to here, suppose 0 to 5. So we will discuss these things later, inshallah. But today, since this is the first class of your after your break, so that is why I did not go very fast today. And also I have given you a video to get you attracted. But the thing is that okay, right now 38 students have joined. But CR, please tell the other people to join every day, every Thursday. Okay, and if I told you, if you are not interested from my part, no problem at all. And I will be very glad because I don't need to come. Yeah? And at this age, who wants to come, you see, to teach you? Anyway, let me take your attendance.